Tantor Audio, a division of recorded books, presents The One Thing You Need to Know, the simple way to understand the most important ideas in science, by Chown, narrated by Peter Noble. Foreword. I am the wisest man alive, for I know one thing, and that is that I know nothing. Socrates. I was born not knowing, and have only had a little time to change that here and there. Richard Feynman. Recently I was asked to give a talk to a law firm about quantum computers. Warned that I could not assume any scientific knowledge in my audience, I thought, what is the one thing you need to know to understand quantum computers? The one thing from which everything else follows? As I put together my presentation, it occurred to me that I could do exactly the same for a myriad other scientific concepts, and that in a world where most people are time poor, telling them the one thing they need to know to understand a topic and showing how everything else follows as a logical consequence might be a novel and fun way to communicate a lot of deep stuff in a compact and digestible form. Einstein's special theory of relativity is a consequence of the fact that a beam of light is uncatchable. Similarly, much of quantum theory is a consequence of the extraordinary fact that the ultimate building blocks of matter, atoms and their constituents, can behave both as localized particles and as spread-out waves. The standard model of particle physics, the high point of 400 years of physics, is a result of nature's mysterious obsession with enforcing local gauge symmetry. Admittedly, that's a bit more of an esoteric thing. Of course, not all subjects are as clear-cut as this, and with complex subjects like human evolution and the brain, not everything quite follows from one single thing. But with this proviso, I have tried my best to provide a way into 21 topics, from global warming to the Higgs particle, from electricity to the Big Bang, from black holes to evolution by natural selection. I hope you enjoy it. Chown. 1. Gravity. Every piece of matter exerts an attractive force on every other piece of matter. I can calculate the motion of heavenly bodies, but not the madness of people. Isaac Newton. Gravity is a universal force of attraction, which means that it acts between every chunk of matter and every other chunk of matter. There is a force of gravity, for instance, between you and someone passing you on the street, and there is a force of gravity between you and the coins in your pocket. You do not notice either of these things, however, because gravity is such a phenomenally weak force. It probably does not seem so. After all, it is hard to jump more than a meter in the air before being pulled back down to the ground. Nevertheless, gravity is puny. Hold your arm out horizontally. The gravitational force of the entire Earth, countless quadrillions of tons, cannot pull your arm down. Despite its fundamental weakness, gravity has the property that it gets bigger the more matter there is. Unlike nature's electromagnetic force, which can be both attractive and repulsive, so that in all normal matter it cancels out, gravity comes in only one form, which is always attractive. Consequently, gravity's effect is cumulative. The more matter there is, the more gravitational attraction. This is why gravity plays no discernible role on the scale of the coins in your pocket or of people passing you in the street, but is significant for large bodies, such as planets, stars, galaxies, and the universe as a whole. In fact, it is possible to deduce the threshold size at which gravity becomes dominant. Take an atom, which consists of a positively charged nucleus about which negatively charged electrons orbit. It is the repulsion between the orbiting electrons of one atom and the next that keeps them apart and keeps matter stiff. In the simplest atom, hydrogen, which consists of a single proton orbited by an electron, the gravitational force between them is about 10 to the power of 40, or 10,000 billion 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 times weaker than the electromagnetic force. Consequently, when a body contains more than about 10 to the power of 40 atoms, the force of gravity beats the electromagnetic force. For a body made of rock, 10 to the power of 40 atoms corresponds to a diameter of about 600 kilometers, and for a body made of ice, which is easier to squeeze, the equivalent diameter is about 400 kilometers. If the force of gravitational attraction is dominant, it will pull all the matter into the most compact form possible, which is a sphere. So the prediction is that all rocky bodies in the solar system bigger than about 600 kilometers across will be spheres, while all that are smaller than this will be potato-shaped. For an icy body, the corresponding threshold is about 400 kilometers. And, sure enough, looking out across the solar system, this prediction is indeed borne out. The original template for the force of gravity was actually magnetism. In 1600, the English scientist William Gilbert experimented with naturally magnetized chunks of magnetite. He found that the greater the mass of such a lodestone, the greater the attraction it exerted on a piece of iron. He also showed that the attraction is mutual. That is, the force of attraction exerted by a lodestone on a piece of iron is exactly as strong as the force of attraction exerted by the iron on the lodestone. On the basis of this, Gilbert suggested that magnetism might be the force holding the solar system together. Robert Hooke, Isaac Newton's greatest rival, was much taken by Gilbert's findings. However, he realized that the force holding the planets in the grip of the sun could not be magnetism, since bodies, when heated, lose their magnetism, and the sun is clearly very hot. Hooke nevertheless saw magnetism as a model for the force that is orchestrating the motion of the bodies of the solar system. Like magnetism, gravity reaches out from one mass across empty space and grabs another mass. Like magnetism, the bigger the force, the bigger the masses involved. And, like magnetism, it is a mutual force. The clues to the detailed behavior of gravity lay in the planetary laws of Johannes Kepler. Between 1609 and 1619, the German mathematician pored over precise naked-eye observations of the planets made by Danish astronomer Tycho Brahe from his observatory on the island of Hven. Eventually, after a gargantuan effort, he deduced 3 laws that govern the behavior of the planets. Kepler's second law of planetary motion recognizes that a planet travels more quickly when nearer the sun, and more slowly when further away. More precisely, it states that an imaginary line joining a planet to the sun sweeps out equal areas in equal times. This area is proportional to the speed of a planet times its distance from the sun, a quantity in modern parlance known as its orbital angular momentum. This quantity is constant, Newton realized, only if the force on a planet is directed solely towards the sun, and there is no component whatsoever along the path of a planet. Consider for a moment how extraordinary this is. Before Newton, almost everyone who had ever wondered about the motion of the planets imagined a force actually pushing them around in their orbits, provided perhaps by angels flying alongside the planets and blowing them along or chivying them with their beating wings. Newton, however, saw the message in Kepler's second law. No force is driving the planets around in their orbits, Instead, they are in motion solely because of their inertia, the tendency of a body in motion to stay in motion. It was something Newton encapsulated in his first law of motion. A body stays at rest or moves at constant speed in a straight line unless acted upon by a force. On Earth there is always a force acting on any body, such as the friction slowing a kicked football, but in the absence of such a force, the football would carry on in a straight line forever. Armed with his insight, Newton was able to pin down exactly what the force of gravity, directed always towards the sun, does to a planet's trajectory. It continually drags it away from its natural straight-line path, and in doing so, it traps it in eternal solar orbit. Newton now had to identify the precise character of the force of gravity, how it varied in strength with distance from a massive body like the sun. He was able to do this because of his guess that gravity is universal. In other words, that the force that acts on a planet is the same force that acts on an apple detached from a tree. Such a proposal was radical and courageous because it flew in the face of the Church's teaching that the heavens were not only made of a different essence to the earth, but also danced to the tune of different laws. But it enabled Newton to directly compare the strength of the Earth's gravity acting on a falling apple with the strength of the Earth's gravity acting on the moon. Knowing how far away the apple was from the center of the Earth, and how far away the moon was from the center of the Earth, he could then determine how the force of gravity changed with distance. At first glance, it appears impossible to compare the force of the Earth's gravity on an apple and the moon, because the apple is falling and the moon is not. However, it was Newton's genius to recognize that appearances are deceptive, and the moon is, in fact, falling. Newton imagined a cannon firing a cannonball horizontally. As it flies through the air, it is pulled downwards by gravity and hits the ground after travelling, say, 1/2 kilometre. He then imagined a larger cannon that fired a cannonball even faster, so that it hit the ground after travelling, say, 5 kilometres. Finally, he imagined a super cannon that shot a cannonball at 18,000 kilometres an hour. At this enormous speed, as fast as the cannonball falls towards the Earth's surface curves away from it, so it never hits the ground. In fact, it falls forever in a circle. The moon is doing precisely this. It is falling towards the Earth as surely as an apple falls from a tree. The surprising answer to the question, why do the moon and Earth-orbiting satellites not fall down, is therefore that they are falling down. It is just that they never reach the ground. Newton estimated the acceleration of the apple by timing its fall, and he estimated the acceleration of the moon from how far it fell towards the Earth in the same time. He compared the two, and knowing the distance of both the apple and the moon from the center of the Earth, deduced that gravity weakens according to an inverse square law. In other words, if two massive bodies are moved twice as far apart, the force of gravity between them is 4 times as weak. If they triple their separation, gravity becomes 9 times as weak, and so on. For his next trick, Newton demonstrated that a planet experiencing a centrally directed inverse square law of gravity orbits the sun in an ellipse. It was Kepler who had discovered that the paths of the planets around the sun are ellipses, and not circles, as the Greeks had believed. He had enshrined this in his first law of planetary motion. A planet travels in an ellipse, with the sun at one focus. Note: the foci of an ellipse are 2 fixed points on its long axis. Their locations are such that for each point on the ellipse, the sum of the distances from the point to the two foci is a constant. End note. Newton turned his mind to explaining Kepler's first law in August 1684, when Edmund Halley visited him at Cambridge, hoping to settle a dispute between his friends Robert Hooke and Christopher Wren. Hooke maintained, without proof, that if the force of gravity was directed towards the sun and obeyed an inverse square law of gravity, then the path of a planet would be an ellipse, as Kepler had found. Newton told Halley that he had obtained a proof that it was indeed an ellipse. However, despite searching high and low in his rooms at Trinity College, he could not find his calculations. Halley's visit not only prompted him to redo his calculations, but also spurred him to embark upon a 2-year write-up of decades of his unpublished work on gravity and motion, in what would become one of the towering achievements of science, the Principia. Newton in fact proved that bodies under the influence of centrally directed inverse square law of attraction move not in an ellipse, but more generally in a conic section. Think of a cone standing on its base, and a sharp knife slicing clean through the cone. If the knife simply cuts through the cone from one side to the other, the exposed cross-section is elliptical, and if the slice is parallel to the base, it is a circle, which is a special case of an ellipse. If the knife cuts down through one side of the cone and out through the base, parallel to the other side of the cone, the exposed cross-section is an open-ended parabola, and if the knife cuts down through one side of the cone and out through the base vertically, the result is an open-ended hyperbola. The 3 types of path correspond to 3 different physical situations. If a body has insufficient speed or energy to escape the sun, it will be trapped forever in an elliptical orbit, as the planets are. However, if it has sufficient energy to escape, it will follow a hyperbola, flying off to the stars. The parabola is the path of a body that sits on the knife edge between being bound and unbound. It can escape the sun's gravitational tyranny only by putting an infinite amount of distance between it and the sun, which would take an infinite amount of time. Armed with his law of gravity, Newton was not only able to explain the motion of the moon around the earth and the movement of the planets around the sun, but also the tides in the oceans. These are caused principally by the moon and the sun. Tides are created not by gravity, but by differences in gravity. Take the moon. Because its gravity weakens with distance, when an ocean is facing the moon, the water at the sea bed experiences a weaker tug than that at the surface. This difference causes a small upwards bulge in the ocean. As the Earth turns on its axis, the bulge moves through the ocean, causing the sea level to rise and fall at the seashore. However, this explains only one of the 2 tides a day. The other is caused because on the far side of the Earth from the moon, the water at the sea bed, being nearer the moon than the water at the surface, experiences a stronger tug than the water at the surface. The difference stretches the water at the surface away from the water at the sea bed, creating a second bulge in the ocean. Actually, at any location there are 2 tides, not every 24 hours, but rather roughly every 25 hours. This is because the moon does not simply hang static in the sky above one place on the ocean, while the Earth turns under it. Instead, it circles the Earth in the direction of the Earth's rotation, taking 27.3 days to make a circuit. It means that a point on the ocean directly under the moon will not be directly beneath the moon again after 24 hours. For the point on the ocean to be directly below the moon again, the Earth must rotate a further 1 divided by 27.3 of a complete turn, which takes 1 divided by 27.3 of 24 hours, or about 53 minutes. Consequently, 2 tides are experienced not every 24 hours, but every 24 hours and 53 minutes. The tides pulled by the moon are twice as big as those pulled by the sun, from which Newton correctly deduced that the moon is twice as dense as the sun. This is a truly remarkable result. It holds only because of a peculiar cosmic coincidence. At this particular moment in time, the moon and sun appear the same size in the sky. Incidentally, this coincidence also means that we are periodically treated to a total eclipse of the sun, when the disk of the sun is totally blotted out by the moon. Such a spectacle, however, has been visible only during about 5% of the history of the Earth, since the moon is receding from the Earth. Currently, it is moving away at about 4 centimeters a year, as determined from the flight time of laser pulses fired from Earth, which bounce off corner cube reflectors left by the Apollo astronauts in the 1970s. Tides occur not only in the Earth's oceans, but in its rocks as well. These cause a strange effect, first noticed in about 100 BC by the Greek philosopher Posidonius. Water in a well rises at low tide and drops at high tide. An explanation was finally provided in 1939. Wells are obviously dug into waterlogged ground, and when the tide is high, the ground bulges upwards, sucking water out of the well like a sponge. When the tide is low, the ground falls back, squeezing the water out of the sponge and back into the well. The exact difference in the water level depends on several variables, but can be as much as a meter or so. Another phenomenon caused by rock tides was noted by physicists at CERN, the European Centre for Particle Physics near Geneva, in 1992. Their electron-positron collider, or LEP, was a huge underground ring-shaped tunnel running through the rock. The physicists noticed that twice every 25 hours there was an increase in the speed or energy of the electrons and positrons flying around their subterranean racetrack. For a while they were deeply puzzled, until someone realized that tides were causing the rock in which the tunnel was buried to bulge upwards and fall back down, expanding and contracting the LEP ring by about 1 millimeter in length twice every 25 hours. Perhaps the most striking example of rock tides, however, is on Jupiter's pizza-like moon, Io. The violent tidal stretching and squeezing of the moon by the giant planet Jupiter, plus the other nearby moons, has heated its interior, liquefying it and making it the most volcanic body in the solar system. In fact, pound for pound, it generates more heat than the sun. Newton's law of gravity undoubtedly has huge predictive power. However, it breaks down in certain circumstances because, as Einstein realized in 1915, the source of gravity is not actually mass, but energy. Mass energy is certainly one form of energy, but there are others too, and they also have gravity. In particular, close to the sun, where gravity is stronger than anywhere else in the solar system, the energy stored in the gravitational field itself has gravity. This means that gravity is slightly stronger than Newton would have predicted, and explains an anomaly in the motion of the solar system's innermost planet, Mercury. The planet does not orbit the sun in a standard ellipse, but in an ellipse which continually changes its orientation, or precesses, tracing out a rosette-like path. Just as Newton's law of gravity breaks down, Einstein's theory of gravity the general theory of relativity, itself breaks down. This happens at the heart of a black hole and in the Big Bang, where it predicts a nonsensical, infinitely dense singularity. The expectation is that a quantum theory of gravity will fix this problem. Currently, the only framework that unites a theory of gravity, though not necessarily general relativity, with quantum theory is string theory. This views the fundamental particles not as point-like particles, but as vibrating strings of mass energy living in a 10-dimensional space-time. Such a theory also permits the existence of 2D, 3D, 4D objects known as brains, and these may have a bearing on one of the outstanding puzzles of gravity. Many physicists believe that the four fundamental forces of nature are merely aspects of a single superforce. But it is hard to imagine a single formula that describes such a force that would result in one, gravity, being at least 1,040 times weaker than the others. String theory suggests a possible way to address this conundrum. Perhaps our universe is a three-dimensional island, or three-brain, floating in 10-dimensional space-time. If all the forces are pinned to our three-brain, but gravity alone leaks out into the 10-dimensional bulk, it would be diluted in strength, neatly explaining why it is so mind-bogglingly feeble. 2. Electricity. By exploiting a force 10,000 billion times stronger than gravity, we power the world. Bring in the bottled lightning, a clean tumbler, and a corkscrew. Charles Dickens. Electricity lights the homes of billions of people across the world. It provides the energy for washing machines, TVs, toasters, and mobile phones. In the future, it is likely that electricity will also power billions of cars on our roads. The reason electricity can do all this is down to one thing: the mind-blowing strength of nature's electric force. To get a feel for the strength of the electric force, imagine a mosquito. It is made of atoms like you and me and everything around us. The nucleus of an atom has a positive electric charge, and the electrons have a negative charge. Unlike charges attract, and it is the attraction between a nucleus and its electrons that glues together an atom. Now, imagine it is possible to magically remove all the electrons in the mosquito. Only the positively charged nuclei remain. Like charges repel, so all the nuclei fly apart. The mosquito explodes. It explodes not with the energy merely of a sparkler or a stick of dynamite, or even a hydrogen bomb, but of a global mass extinction. That is, the energy equivalent to that of the city-sized asteroid that slammed into the Earth and wiped out the dinosaurs 66 million years ago. The reason for this is that the electric force is an extraordinary 10,000 billion times stronger than gravity. Remarkably, we do not notice such a phenomenally powerful force because in everyday matter there is an equal quantity of positive and negative charge. So the force of electric repulsion is exquisitely balanced with the force of electric attraction, and they perfectly cancel each other out. Which is why when you walk past someone in the street, you are not attracted or repelled by them, and there is not even the remotest hint of a force 10,000 billion times stronger than gravity operating in both of you. If, however, it was possible to create a charge imbalance, as with the mosquito, it would unleash the phenomenal power of the electric force. And this...
Sample complete. Ready to continue?